Alright, what are we going to make today? The blinking lights? Nah. Ooh. Op amps. How about a Wien bridge oscillator? That sounds like fun. So here's our typical Wien bridge oscillator. But before I get started, I just want to say that today's video is sponsored by PCB. If you've got a circuit design like this, you draw it up in your EDA software, zip up the Gerbers, and send it to them. For $5, they'll do you up 5 boards in about a week. Now, shipping, of course, is added on top of that. And 5 boards coming to me here in the United States generally costs about $24. But hey, that's worth it. They do really nice work, as you'll see later on in our video. Now here is our Wien bridge oscillator. And it generates sine waves, which is different from some of the other oscillators we've dealt with, like the 555 and an astable multivibrator using the transistors. Those are basically on-off type. Digital. This is going to ramp voltage up and down, and it's going to generate sine waves. Now you can think of this as a positive gain amplifier, okay, with a band pass filter. So there's our band pass filter. And then we have our positive gain amplifier, and it has positive feedback coming through here. Now, it also has an automatic gain control in the form of an incandescent light bulb, which as it gets warmer, the voltage drops. So we have an op amp here, and you're going to have to imagine there's positive and negative connections. And then this is our gain control here coming off of that little negative feedback loop there. And then our frequency is going to be controlled right down here. My camera decided to eat the piece of footage where I explained the frequency is equal to 1 over 2 pi RC, and then I said we would go and take a look at it in the simulator software on the computer. So let's go do that. I apologize for the loss of footage. Okay, this is multisim. That we covered in a previous video. So I'm going to draw up the circuit, but I'm going to add a couple more things to it. I'm going to add some face-to-face Zener diodes. And what they're going to do is they're going to help us prevent saturation. You see, if the positive feedback gets too much, it can saturate. So the two Zener diodes are placed face-to-face, and they're connected across the upper resistor, which I haven't drawn in yet, but it's going to be about 22K. And when the output voltage rises above the Zener's breakdown voltage, one or the other of the Zeners will conduct, depending on which one is matched to the polarity of the feedback at the time. So it's going to shunt it, basically. And that's going to cause the resistance of the negative feedback to decrease, and more negative feedback is applied to the op amp, and then that will help us kind of control the output voltage a fair bit. So that's what I'm drawing here. The second change we're going to put in is a potentiometer to adjust the negative feedback again, just to help kind of smooth things along. Otherwise, it's the same circuit. So for the op amp, forget what I'm using. Hold on a second. Yeah, we're going to go with an LM741 or an equivalent, whatever we have. So the part that I just drew there is going to be our RC timing circuit that is going to determine our frequency. So, and that's what we looked at in that little title I showed you there. The frequency equals 1 over 2 pi RC. So these are our starting values: 1 microfarad, and 1K. But they may not be our finishing values. We'll have to put them in a moment. Now, what we're bringing up here is that bandpass filter part. And that's going to help us just kind of weed out frequencies that don't match up with our RC part. So like at a particular frequency, like we said, that 1/2 pi RC, the inverting input voltage and the non-inverting input voltage will be equal and in phase. So the positive feedback is just going to cancel out any negative feedback and the circuit will oscillate. But if we go to any other frequency, then our first voltage is going to be too small to cancel out the second voltage and it won't oscillate. So the gain has to be positive, +1, +3. And our resistors have to satisfy the condition R3 divided by R4 is equal to 2, and that'll give us a non-inverting gain of 3. Anything less than this value is going to cause the oscillations to cease, and anything more will cause the output to saturate. So it's kind of crazy, and that's why we go ahead and we put in those Zener diodes to control the top end, and the potentiometer to kind of go ahead and control the bottom end of everything. Now we can test it out. Okay, again here, let's take a look at the pieces of our circuit here. So right here is what we'll call the frequency generator, or the oscillator part, for lack of a better term. And then this part will be our band pass filter. This is our positive voltage supply, our negative voltage supply. There is our potentiometer to adjust the feedback. And then there are our opposing Zener feedback. So I'm going to run this simulation here. And if you take a look over here, you can see the circuit is not oscillating. If we bring in the split, you can see no oscillation is occurring there at all. So let's bring up R4, say 1.5. Come on. Oh, so close, and yet so far. There we go. We're still not seeing any oscillation. Let's change our capacitor. Still not seeing any oscillation. Oh, there we go. Now we're getting some oscillation, which is what we want to see. Okay, there is a better view of the circuit in action. Now let's see. Put some cursors there. So we're getting an oscillation of 303 hertz. So it looks good. This is a viable working circuit. Now let's whip it out in some EDA software. Okay, there is our same circuit whipped up. You can see down here is our op amp. Here is our oscillator part, our bandpass filter, and our feedback controls. The only difference is I've added in some headers here so that we can take it to a PCB. Here we can see our PCB. There is our top layer. There is our bottom layer with our copper pour, our top silk, our bottom silk. And all we have to do now is knock out our Gerbers. Let's take a look at this in 3D mode. Alright, there we have her. I'm going to use male pins here instead of these females, but you get the idea. Alright, all I got to do now is order up my Gerbers from PCB Way and wait a few days until they arrive. I'm excited. And works. Through the magic of video editing, 7 days have passed, and our boards have arrived. So let me whip one together here right quick. Okay, so there she blows. I didn't have a 741 on hand. I thought I did, so I switched it out for a 357. They are pin compatible op amps, so we shouldn't have too much trouble there. I also have my split rail voltage supply ready to go. However, I can't remember exactly the order of these. I'm pretty sure that one down there is pin 1. Yeah, square, it's pin 1. So we will tone them out. Make sure I don't plug anything into the wrong spot. Okay, so pin 1 is my positive voltage. That should go to pin 7 on the op amp. Good. Then my negative voltage should be pin 4, right here. Yep. And then the output on pin 6, which means that one is ground. Okay. So let's look here. So blue is our positive voltage and purple is our negative voltage. And I need different connectors. Okay. Female on both ends. So we will go positive is red, negative shall be brown, and black will be our ground. So red, brown, and ground. Okay. So then we need a wire for our output. One of these will work. We'll do yellow. This is our output wire. Almost set, but I need somewhere to connect the ground for the scope. I didn't think of that. Rats. One moment. Okay, I just tacked on a piece of wire there. Alright, got the scope ready to roll. So our signal goes to the yellow wire. Excuse me. Ground goes here. Power supply to be set. And where my power supply wires at. Okay, power supply wires. Yellow is plus, green is minus. And it's kind of hard to reach over here. That's unfortunate. What's going on? Oh, we got something now. Let's see here. Try not to bump the camera while I do this. A little jitter there, but let me turn out the light here. Hold on one second. Make it easier for you guys to see. My trigger. Alright, so where are we? Let's take you out of the holder here. I gotta get closer to the thing so I can read the numbers. Okay. Let me math this out for us. I'm getting 308.5 hertz. We figured from the simulation 330, but you know, there you go with you know, your tolerances and everything. Nothing is ever exact. You know what they say? If you can't make it exact, at least make it adjustable. So there she is, a simple sine wave generator, purely for demonstration purposes. A Wien bridge oscillator. I hope you guys enjoyed this. If you did, please give me a thumbs up. Feel free to comment, share, and don't forget to subscribe. Big thanks to the patrons. Big thanks to PCB Way for sponsoring the video. And a big thanks to you guys for watching. Hey, if you're not too busy, hop on over to Teespring and grab yourself a little something. That's it. I'm out. Peace. I want to thank you all for watching and spending time with me today. A community like this is something that we can all be very proud of. So again, thank you very much for all your support of Learn Electronics. Please feel free to check out the Patreon page. $1 a month is all I ask, and Really helps keep the channel alive. We also have an Amazon shop where you can buy most of the items that you see on here, and there's a link to it down below.